Good afternoon, everybody. Welcome to the lecture for Friday, March 20th. Today we're going to continue with Chapter 1. We're going to start Chapter 1.6, and hopefully we'll finish it on Monday. And the last section of Chapter 1, Section 1.6, just further investigates certain properties of modular arithmetic. Maybe as a bonus content, I'll talk about the codes part of the section, which I'm not going to test you on, but is interesting. It's an interesting application of some of the things we've been talking about. So without further ado, let's get into the material. So the main thing that we've been talking about so far is sort of what happens with all the algebra stuff we've been talking about with modular arithmetic. So can you solve linear equations? How many solutions are there? Are they still unique like they are for the integers and rational numbers and things like this? And our first theorem deals with a similar topic, but it's really sort of the first thing that doesn't have an analog, I would say. And that has to do with the order of elements. So this is the first theorem we're going to prove. Theorem 1.6.1. So number A is invertible modulo n. So if I consider the equivalence class modulo n, this thing is invertible if and only if, for some power of A, I get to 1. And the smallest such number is called the order of A. So an element has an order if and only if it is invertible. Otherwise, the order isn't defined. So what's the picture here? Let's just draw an example of what's going on before we go into the proof. So for instance, if I consider 2 mod 9, let's compute the order of 2. Well, 2, when I multiply by 2 again, goes to 4, which is still mod 9. 4 times 2 goes to 8. 8 times 2 goes to 16. 16 mod 9 is 7. 7 times 2 goes to 14. 14 mod 9 is 5. 5 times 2 is 10. 10 mod 9 is 1. So the order is, this is 2 to the first, second, third, fourth, fifth, sixth. So the order of 2 is 6. Since none of these are congruent to 1, but when I take 2 to the sixth, I finally get to 1. 2 to the 6th is 64. So 64 is 63, which is 7 times 9 plus 1. So that's the content of this theorem. This picture makes sense, and we can do this process to compute the order of a number, if and only if that number is invertible, which is equivalent, as we know from before, an element is invertible if and only if it's coprime with the modulus. So because 2 is coprime with 9, it has an order and it's invertible. These are all equivalent conditions. So let's go into the proof. So the first thing we need to do, there's two conditions, right? This is an if and only if condition. So first we'll assume that A has an order, so that there is some k such that A to the k is congruent to 1 mod n, and this is the easier direction, and prove that it's invertible. And then if it's invertible, we'll then prove that it has an order. So the first step is to assume, and sometimes people write things like this to indicate what direction they're doing. So here I'm assuming the right-hand side, which is there exists this k, and then I'm going to prove the left-hand side. So assume that there exists a k such that a to the k is congruent to 1 mod n. Okay, so it's very easy now, because then a times a to the k minus 1 is congruent to 1 mod n. So a to the k minus 1 is just a inverse. Right? The inverse was just defined to be some number such that when I multiply it by a, I get something congruent to 1 mod n. So it's just exactly given to us by this equation. Once I have this equation, I know that the inverse is this k minus first power. Which is very interesting, right? Because it's a bit surprising that if you have an inverse, it's always given by some power of a. It's not obvious, but it is obvious from this proof, but it's something you wouldn't expect initially. Okay, so I promised that was the easier part, so let's now do the harder part. Now I want to assume that a is invertible modulo n, and I want to find some k such that a to the k is congruent to 1. And here we're going to use something we used before, which is called the pigeonhole principle. And what do I want to do? So recall that I can only find n congruence classes in modulo n. All right, 0 up to n minus 1. So what do I want to do? I want to consider the sets a squared, a cubed, a to the n plus 1. It's a set, and this set has n elements. N plus 1 elements. It's important. So because there are more elements here than there are congruence classes, this is where the pigeonhole principle comes in. There are two distinct powers of a which have the same. So there exist two different numbers, k and l, such that, and I write not equal here to emphasize the fact that these are two distinct numbers, a to the k is congruent to a to the l modulo n. Okay, so now what do I need to do? I need to use, this is where I can actually use my assumption, right? In this part of the proof, I'm assuming that a is invertible modulo n, and I want to prove it has an order. So far, I haven't used that fact. This is always true, that you can find some power of a that's equal to itself. But I want to use the fact that a has an inverse, and therefore a to the l has an inverse. So since a is invertible, we can multiply each side of the equation. Multiply each side of the equation by a to the minus L. Therefore, a to the k minus L is congruent to 1 modulo n. And so some power of a is congruent to 1, and it's not necessarily the order, because the order is the smallest power, but I have at least one power of a that's congruent to 1 modulo n. So this is the proof that an element is invertible if and only if it's congruent to 1 modulo n, if and only if its GCD with n is equal to 1. It's coprime with n. So on next week's homework, probably, there'll be some problems asking you to check the order of elements and problems related to orders of elements. Okay, so that's our first theorem. What's our next theorem? Our next theorem says that if an element has some order, k, then two powers of a are congruent if and only if their powers, the exponent, is congruent modulo the order of the element. So the picture is exactly, it's sort of intuitive from this computation here, this picture, right? What happens when I start multiplying by 2 again? I come back to 2. Right, so 1, 2. So if I start from here and I take some power, I need to go around the loop a certain number of times. So this is 2 squared, right? So to be able to be congruent to 4, some power of 2, I would need to take a power of 2 and then go around the loop as many times as I want, and that's the order, right? So the order here is 6, so I can 2, as long as I'm 2 mod 6, the power, I'm going to end up at 4 mod 9, because I'll just keep going around this loop until I end up at 4 again. Okay. So again, this is an if and only if statement. So I have 2 things to prove. The first thing I have to prove is that, again, the easier thing will be the right-hand side to the left-hand side. I'll prove that if R is congruent to S mod K, then I have this congruence. And the second thing I'll prove is that if I have this congruent, then R is congruent to S mod K. And it's exactly this cycle picture. So proof. So we'll do this way first. So assume R is congruent to S mod K. Then, just by definition, K divides R minus S, or R is equal to S plus some multiple of K for some L in Z. Well, now what do? I just plug it in, right? So, a to the r, this is just equal to a to the s plus kl, which is equal to a to the s times a to the k to the l. This is just exponent rules. But what do I know? I know that k, by definition, is the order of a. So these things, each time I multiply by a to the k, I'm just multiplying by 1 modulo n. So this is just a to the s modulo n. right? So this is the picture that I showed before, right? I know that I'm congruent to R, S is congruent to R, so going along R times is the same as going along S times, and then going along the loop a certain number of times. And each time I go around the loop, if I go around the loop L times, each time I go around, I'm multiplying by 1. So I get back to a to the S. So I hope this is clear. Now let's prove the opposite implication. So I want to assume that a to the r is equal to a to the s modulo n, or congruent rather. So again, I start with the assumption. Well, we just showed that if A has an order, right? We're assuming that A has order k. If A has an order, it's invertible. So since A has an order, this is just exactly the previous theorem that we just proved. So since A has an order, A to the r minus s is congruent to 1 mod n. I just multiply by a to the minus s on both sides of my congruence. So now what do? I divide r minus s by k. What's a good letter here? Normally I would use r for remainder, but we've already used r. So let's say plus n. And if I can show that n is equal to 0, then I win. And the division algorithm tells me that this n, this remainder, is less than the thing I'm dividing by, which is k. So this is just division with remainder. So what do I know? Well, if I take a to the r minus s, r minus s is kl plus n. But again, I do the same trick that I did before. Not congruent, this is still equals a to the n times a to the k to the l. And this is a to the k just goes around the cycle, right? A to the k is equal to 1. And I do it L times, so this is just still congruent to a to the n. Oops, n was bad. Let me change it to m. Sorry about that. M. A to the m mod n. All right, n is always my modulus here. But my assumption is that a to the r minus s is congruent to 1. So a to the m is congruent to 1 mod n. And here's where I use my definition. Where is it? Definition of order. The order of an invertible element is the smallest k, such that a to the k is congruent to 1. And here my m is smaller than k. Therefore, m has to be 0. So k is the smallest positive number, non-zero number. I get that m equals 0. And since m equals 0, I know that r minus s is k times l, which is just to say that r is congruent to S modulo K. So this is the main, the crux of the argument here. And we'll see this argument come up again later on in chapter 4 when we start talking about groups and orders of elements in groups. Really, this is sort of a primer on groups, and we haven't defined that yet, but this is an example of a group, these the invertible elements. Okay, so let me just say a little corollary here. The book doesn't explicitly say it, but I want to. If A has order K, A to the M is congruent to 1 mod N, if and only if K divides M. So the only things that that get you back to 1 are multiples of the order. And that's just what you get here when you take S equals 0. If you take S equals 0, you get A to the R is congruent to 1 mod N, if and only if R is congruent to 0 mod K. And R being congruent to 0 mod K is just that R is a multiple of K. Right? R minus 0 is divisible by K. So this, I think, is the main application, the main way that you apply this previous theorem. Okay. So let's move on to the last theorem for the day. And this theorem has a name. It's called Fermat's theorem. So this says, let P be a prime, and assume that A is a non-zero element. Then the order of A divides P minus 1. It's a very nice theorem. We know the order of elements in a prime modulus. Or we don't know the order exactly because it could divide P minus 1. But it's we know that exactly this. Okay, the book says it slightly differently. This is actually the corollary. And my first statement in the proof of the theorem will be to reduce to prove what the book says. So how do you prove this theorem? So by the previous, it suffices to show that A to the P minus 1 is congruent to 1 mod P. Because if I show this, then I know that P minus 1 has to be divisible by the order. Right? That's exactly the corollary that I just wrote, this one. So if I can show this, then I get the result. So how to show this? So notice first that since P is prime, every non-zero element is coprime with P. The elements 1 up to P minus 1 are all coprime with P, and therefore invertible. Now let's consider the map. Let's define a function here. Define a function f from this set back to itself by f of x is just multiplication by a. And I consider its congruence class, mod p. So the claim is that f is a bijection. And it's exactly because it has an inverse. And in fact, it's a two-sided inverse. So if I multiply by a and then multiply by the inverse of a, I'm just multiplying by 1, so I get back to where I start. And if I multiply by the inverse of a and then a, I'm doing the same thing, because multiplication commutes. It doesn't matter if I multiply by a and then a inverse, or a inverse and then a. So this function has to be a bijection because it has an inverse, a two-sided inverse. Which means that the set sets 1 and p minus 1 and the sets a times 2, a times 3, a times p minus 1, these are the same sets. They're just renamed. This is put in a different order, but the same of the elements here are the same as the elements here. So if I multiply all of the elements here, and I multiply all of the elements here, I get the same answer, because it doesn't matter what order I multiply elements in. So because these sets have the same elements, the multiplication 1 times 2 times 3 all the way up to p minus 1, it's not only congruent, it's in fact well, no, it's congruent, right? Because they're the same sets modulo n, modulo p rather. I should emphasize that they're only the same sets modulo p because everything needs to happen mod p. When I multiply by a, I probably leave this set. I need to use the division algorithm to get me back to these canonical representatives. So when I multiply 1 up to p minus 1, it's congruent to a times 2a times 3a times all the way up to p minus 1a mod p. And now maybe you see what we're going to do. I'm going to group all of the a's together. I'm going to pull all the a's to the left-hand side of this. And how many of them are there? Well, I've multiplied from 1 up to p minus 1. So a appears in this equation p minus 1 times. So I'm going to write this with the more commonly used shorthand, p minus 1 factorial is congruent to a to the p times p minus 1 factorial mod p. And now p minus 1 factorial is a product of invertible elements, so it itself is invertible. So I can multiply by p minus 1 factorial inverse and get that here's p minus 1. 1 is congruent to a to the p minus 1 modulo p. And that's the theorem. That's that's the proof. It's a very elegant proof, I would say. And the trick is really using the coprime characterization of invertible elements so that we know that A is invertible. And the invertibility of A tells me that exactly that this list of elements is the same as this list of elements put in a different order. So let's check this ourselves. Just with an example. So let's let P, my prime number, be, say, 9 is not prime, 7. And let's try to prove, I mean, you can check directly that 2 to the 6th is 64, which is definitely congruent to 1 mod 7. So there we go. P minus 1 is 6. So 2 to the 6 should be congruent to 1. 6 should be the order of, or the order of 2 should divide 6. In fact, the order of 2 is 6 here. Oh, no, sorry, it's 3. Because 2 cubed is 8. Okay. So how do we check the proof here? Well, let's just look. We have 1, 2, 3, 4, 5, 6. And then I multiply all these numbers by 2, right? So 2, 4, 6. 4 times 2 is 1, because it's mod 7. 5 times 2 is 3. 6 times 2 is 5. All right, 6 times 2 is 12. 12 minus 7 is 5. And you can see that 1, 2, 3, 4, 5, 6 is the same as the list of numbers 1, 2, 3, 4, 5, 6. So I hope this gives some intuition as to why this works. So I multiply by 2 to get from here to here. And then let's just also check that our bijection proof works as well. How do we get back to here? We need to multiply by the inverse of 2. The inverse of 2 mod 7 is 4. So it's times 4. And indeed, 2 times 4 is 8, which is 1. 4 times 4 is 16, which is 2, because 16 minus 14. 6 times 4 is 24. 24 minus 21 is 3. 1 times 4 is just 4, so we're good there. 3 times 4 is 12. 12 minus 7 is 5. And 5 times 4 is 20. 20 minus 14 is 6. So when you're working with modular arithmetic, this invertibility is very nice. And that's the main thing we used in this proof of Fermat's theorem. So Fermat's theorem has more general feature when we look at groups. And we'll look at groups starting with chapter 4. So once we're done with chapter 1. Okay, so this is all I wanted to cover today. Please don't hesitate to email me if you want some more explanation. I can post another video about each of these theorems. I'm also happy to talk with office hours if you had trouble following the proofs. I hope you all are doing well. I hope you all have a nice weekend. And I will be back with another video on Monday. Bye-bye.